right, this video is covering the second part of integration by parts. If you haven't watched the first video, you should watch that first because that contains the main idea of integration by parts. Today we're going to talk about some other things that can happen in an alternate way to do integration by parts when you have repeated cases. So the last example that we worked on yesterday, or in the previous video, was something where we did integration by parts, but then we had a simpler integral, but it wasn't simple enough yet to do the shortcut. So this problem right here, where we went from x squared sine x, we did integration by parts and got x cosine, which at least went from x squared trig function to x trig function, but then we had to do another integration by parts to go the rest of the way to just an integral of trig function, which we could do with a shortcut to finish. Right, so frequently that will be the case, but whenever you have this specific combination is the main one that you see. If you have an exponential function and a cosine, if you think about it, if I were to put either of these as the u, then that means the derivative is not going to change form, right? The derivative of the e to the 4x is going to be just a copy, maybe fixed up with a constant, but that changes with the derivative from e to e, and cosine goes from cosine to sine. If you were to take another derivative, it would be cosine. And the same thing is true whether you're doing the derivative or the antiderivative. The derivatives and the antiderivatives don't get simpler. Right? So in that case, what do you do? Well, you can just pick. It doesn't really matter which one. Pick one to be the u. Let's do the cosine of 2x as the u, although this will work just as well if we choose the e. And then I'll put the other one, the e to the 4x, as the dv. And then we'll go ahead and do integration by parts. So we do the derivative, du dx here, is equal to the derivative of cosine is negative sine, but the chain rule is going to multiply by a 2. So negative 2 sine of x, of 2x. So du is equal to negative 2 sine of 2x dx. And then over here, we've got the antiderivative. So this is the antiderivative of e to the 4x to get the v. And that is the derivative e to the 4x divided by the chain rule. There's, well, you can think of it as, we'll just do this on this first one. If you had a 4 here, that 4 dx would be what we need, so we need a 1/4 to balance out there. So it's just a copy divided by the constant 1/4. Okay? And then we'll plug into uv minus integral v du. So the uv is cosine of 2x. The v is 1/4 e to the 4x. And then the minus integral of v, which is 1/4 e to the 4x, times the du, which is negative 2 sine of 2x dx. Okay, cleaning this up a little bit, we have a 1/4 and e to the 4x and a cosine 2x outside of the integral. And then we have minus, so that's plus. 2/4 is 1/2. And then an integral of e to the 4x times sine of 2x. Okay, which is not simple enough yet to integrate with a shortcut. So we go ahead and do what we did in that last example of the previous video. We put a bracket around this, and we go ahead and do integration by parts again. Now I'm going to choose the same thing. Since I chose the trig function as the u, I'm going to choose the trig function as the u again. And then do the e to the 4x dx again. So the derivative here is going to be 2 times cosine of 2x. And therefore du is 2 cosine 2x dx. And the antiderivative is, again, v going to be 1/4 e to the 4x. So inside of this bracket, we've got a uv minus integral v du. And that means the uv is, these together are going to multiply to 1/4 times e to the 4x times sine of 2x. And then I have an integral of v, which is 1/4 e to the 4x times du, which is 2 cosine 2x dx. Okay. Now, and then let me simplify this a little bit. So this is 1/4 e to the 4x sine 2x. And then we got minus 2 times 1/4 is 1/2, which I'll bring outside, and we have an e to the 4x cosine 2x. Okay, so let me put the rest of that integral in here. We have the 1/2 multiplier. Oops, that's good. And we've got the 1/4 e to the 4x cosine 2x. All right, so here's the problem. This is not getting simpler, but look at this. This integral of e to the 4x cosine 2x is an exact copy of what we started with. So sometimes when you do integration by parts twice, you get the original integral. So when that happens, what we can do is we can write something a little different here. Let me switch to different color here. The original integral, e to the 4x cosine 2x dx, I'm just going to say that is equal to what we got as our result. So I'm going to go ahead and put all of this in blue. This is, I'm going to multiply this out now. Okay, so this is a half times, oh actually it's this first, it's 1/4 e to the 4x cosine 2x. Then it's this term, which when we multiply this is positive 1/8 times e to the 4x sine of 2x. And then it's, let's see, a positive 1/2 times a negative 1/2, so that is minus 1/4 times the integral of, and I'm going to switch to black here for a second. See why? Because that is the original integral. E to the 4x cosine 2x dx. Okay. So notice this and this are the same. So if you write it out as an equation that the problem you started with is equal to your result that still has an unresolved integral, what we can say is we have one of these integrals on this side and a negative 1/4 of that same thing on this side. So what I'm going to do is I'm going to move this to the other side by adding a 1/4 integral on both sides. So I'm going to add 1/4 just to get it off the side. I will add a 1/4 of the integral of 4 e to the 4x cosine 2x to that side. That will leave, we have a total of 1 plus a 1/4 of these integrals of e to the 4x cosine 2x dx, which, what is 1 plus a 1/4? Well, 1 plus a 1/4 over here is 4/4 plus a 1/4, which is 5/4. So I'm going to change this to be 5/4. So this is 5/4 now. We have 1 plus a 1/4, which is 5/4 of that integral, is equal to, and then on the right-hand side, we have 1/4 e to the 4x cosine 2x plus 1/8 e to the 4x sine of 2x. All right. So basically we're combining like terms by combining these two integrals, the original integral and the result of two integration by parts on the right-hand side together. And then to solve for what we solved for in the beginning, we're just going to multiply both sides by 4/5. That way we get the fraction 1. So this whole thing over here and the left-hand side are multiplied by 4/5. And the result is, let's switch to a new color. The integral of e to the 4x cosine of 2x, which is the original problem, is equal to, if you multiply this in, it's 4/5 times 1/4. The 4's cancel. This is 1/5 e to the 4x cosine 2x plus, and then this would be 4. Let's see, if I multiply this in, I'm going to have a half on the bottom here, so that is 1/10. Right, 4/5, let's just do it on this side. 1/8 times 4/5 is the same as 4/8 is 1/2 times 1/5, which is 1/10. And we have e to the 4x sine of 2x. This is the answer. Now, we still have to put our plus c on the end. All right, so just reviewing what can happen here. If you do integration by parts twice, and the result is an exact copy of the beginning integral, you just say that that whole result is equal to that, so that you can subtract the right-hand side integral off to the left and combine like terms, and then divide out the constant to get the answer. We call this the cyclic result, and this cycles back around to itself. So that's good to know to deal with. AP does like that question, so that's commonly encountered, especially on C-response or on multiple choice. Okay, there's one other topic we want to include to wrap up the integration by parts video here, and that is an optional thing called the tabular method. And this is particularly useful if you have an integral which is going to resolve. So let's review something real quick here. The reason that this cycle occurred is because e and cosine, no matter if you put them on the derivative or the antiderivative side, they never get simpler, right? Whereas this one that we did previously, we had an x squared and a sine. The sine will not get simpler, regardless of where you put it, but the x squared, if you correctly put it into u, the derivative does get simpler. So this will eventually resolve without cycling back on itself. So the tabular method is something that you can use when that happens, when you're going to have to do integration by parts at least twice. It's just a faster way to show the result. So you don't have to use it, but it is allowed even on the AP exam if you wish to do that. So most books do teach this. Right, so the usual method of doing, say, this problem here, x squared e to the 2x would be, let's see, the x squared will get simpler if I put it in the derivative side of the toolkit. The e to the x is not going to change form. So what we could do is we could say u is equal to u is equal to x squared, dv is equal to e to the 2x dx, and then take the derivative here. So the derivative du dx is 2x, which means du is 2x dx. Take the antiderivative in this part of the toolkit, and that makes v e to the 2x divided by the constant, so 1/2. And then I can substitute into uv minus integral v du, and then the u will be x squared 1/2 e to the 2x minus integral of v, which is 1/2 e to the 2x dx for the du. That simplifies to, that cancels to a 1, so now we have minus the integral of x e to the 2x, which worked because it got simpler, but it isn't simpler enough, so we're going to have to do integration by parts again on this part. Right, and for the second integration by parts, we're going to say, all right, the u is x this time, the dv is e to the 2x dx, so the du dx is equal to 1, and that makes the du equal to dx. The antiderivative here gives me that the v is equal to 1/2 e to the 2x again. And then we're going to put uv minus integral v du in here. And we get that this is 1/2 x e to the 2x minus an integral of 1/2 e to the 2x. Right? And that's going to be 1/2 x e to the 2x. When I do this antiderivative, there'll be another 1/2, so that becomes minus 1/4 e to the 2x. And I can put the rest of the integral that that's inside of. I have a minus here, and that's 1/2 x squared e to the 2x. And we'll put our c on there. Distributing that negative, we get 1/2 x squared e to the 2x minus 1/2 x e to the 2x. Minus minus is positive 1/4 e to the negative e to the 2x plus a c. So 3 terms plus the c. Right, so that's the traditional, what you would write to show all the work for traditional two-step integration by parts. So the tabular method is just a faster way to do the same thing. Let me show you what we're doing here. What we're going to do is take advantage of some of the patterns that you've probably recognized here. Like, notice that we go from x squared e to the 2x to x e to the 2x to just e to the 2x, and that the signs are alternating. And what's happening is we keep substituting things in that are derivatives and antiderivatives. So the tabular method recognizes this, and the way you do it is to just write a little table with some columns. First, I'm going to put a column that I call sign, and then I'm going to have a column called u and a column called dv. Right? This is going to start with a plus, and then what I do is I load my u and my dv the same way you would here. So I'm just going to write that this is x squared, and for the dv, I'm just putting e to the 2x. I'll just omit the dx because we're not showing the steps formally. Okay, so just like before, we're going to take the derivative of the u, but we're just going to do it over and over again. We're going to take the derivative. So the derivative of x squared would be 2x, and then I'm going to keep going. The derivative of that would be a 2, and I'm going to keep going, and the derivative of that constant would be a 0. I'm going to take into the dv the antiderivatives, and the first one would be the copy divided by the constant, so that's 1/2. And then have the copy divided by the constant again, which is 1/4 now. Copy divided by the constant again, 1/8. And then the signs do alternate. So if this starts at plus, this goes to minus, this goes to plus, this goes to minus. And then I'm going to build my answer by taking this sign with this u with this dv. The first term is positive x squared times 1/2 e to the 2x. And the next term is a negative term, and that's going to be applied to this u times this dv. So that is 2 times 1/4, which is 1/2 x e to the 2x. And then the next term is positive, and it is this u with this dv. 2 times 1/8 is 1/4 e to the 2x, and then the next term is 0. So instead of that, we'll put the c on, and then we're done. And you get the same result with a whole lot less writing. Right? So this is going to save you time whenever you have to do integration by parts more than twice. It is legal to do this even on the AP exam. But if you do that, you have to have some structure here where the columns are labeled u, dv, so that they can see that you're doing the integration by parts. Okay, so just to finish this up, let me show you where this would be really helpful, where you definitely would want to use the tabular method. Let's say you had x to the 6th e to the x. That would require integration by parts 6 times. And that's a lot of writing to the traditional way. So instead, let's just go ahead and do the tabular method. I'm just going to say we have a sign. We're going to have the u. We're going to have the dv. So this will start at plus. The u is going to be the x to the 6th because that'll get simpler. E to the x will not change. And then we're going to take derivatives on the u column until we get to 0. So this would be 6x to the 5th, 30x to the 4th, 120x cubed, let's see, 360x squared, 720x, 720, and then the derivative of the constant is 0. Okay, over here, all these antiderivatives are e to the x, no multipliers. And the signs alternate, so that's plus, minus, plus, minus, plus, minus, plus, minus. So then we can just go straight to the answer. The first term is going to be that sign with those two multiplied. So we're going to have a positive x to the 6th e to the x. Then we're going to have a negative 6x to the 5th e to the x, a positive 30x to the 4th e to the x, a negative 120x cubed e to the x, a positive 360x squared e to the x. So I should make those arrows so it's clear on the negative signs there. negative 720x e to the x, a positive 720 e to the x, and then a 0. So now it's time to put the constant on. This is the result with a whole lot less writing. So that's where the tabular method would really shine. All right, and that should wrap up everything we need to know about integration by parts. Definitely master this one and use substitution are the main two that we really, really like.